All right, welcome to integration, and we're going to continue talking about integration or antiderivatives, but today we're going to talk about two specific types of examples. We're going to actually look at exponential and logarithmic functions and how to integrate those types of functions. Okay, so the first rule that we have is we're going to look at the integration of the natural logarithm. Okay, and that's when a logarithm has a base e. So to integrate a natural logarithm, we follow this rule, the integration of du over u, and that's going to be equal to the natural log of the absolute value of u plus c, where c is just a constant. So in order to use this type of integration, to do this type of integration, we're going to continue using U-Substitution. Okay, so this is really the key. We're going to be looking to integrate and looking to simplify our problem and get it in the form of du over u if possible. Alright, so our first example is finding the integration or antiderivative of 5dx over x plus 3. So when we first look at this, we're really going to just pick a u value. Now you can use U-Substitution for any antiderivative problem, but however it doesn't always help. Sometimes if you pick the wrong function for u, you get a harder integral. So you have to be really careful when you pick your u value. In this case, we're going to let u be x plus 3. So when u is x plus 3, when you differentiate that, we get du dx equals 1. So that actually means du equals dx. So let's look back at our problem. So we're integrating 5 dx over x plus 3. So let's simplify what we have. Instead of writing dx, we know that dx is equal to du, so we change that. And u is no longer x plus 3, but u is, or x plus 3 is not in the denominator, it's going to be u now because we have that substitution. So in red here is where we substituted what we have. Dx is actually du, and we let u equal x plus 3. So there's our simplified integration problem. So now let's bring the constant, let's bring the 5 out front and leave it over du, 5 times the integration of du over u. And so like we said in that first slide, there's du over u, and we know to integrate that it's natural logarithm. So 5 times the natural log of the absolute value of u plus c. So we apply that rule here. And we wrote that in red. We're not done yet. The last step is just substitute your u back in, and we know that u was x plus 3. So we have 5 times the natural log of the absolute value of x plus 3 plus c. Okay, so here's example 2. We're going to again integrate 2x over x squared plus 1, and we should say dx there. I didn't write that dx, but we can see it here. So integrate 2x over x squared plus 1 dx. Now again, we're going to use U-Substitution. So what am I going to let u be? Probably the denominator. Because if I differentiate that denominator, I know I can get rid of that 2x. So let's look. So we're going to let u equal x squared plus 1. So that means du is actually equal to 2x dx. Now this is different from some of the other problems that we looked at, because we actually see 2x dx. So we don't have to solve this equation here for dx. We can actually leave it as du equals 2x dx. So I've circled that. 2x dx is actually what du equals. So when we rewrite this integral, we have the integral of du over u. We replace 2x dx with du, and x squared plus 1 gets replaced with u, because that's what we let u equal. So right away we see du over u, and there's that natural logarithm integration. So we have the natural log of the absolute value of u plus c, and just substitute your u value in. Okay, so we get the natural log of the absolute value of x squared plus 1 plus that c, that constant. Now, the next example, we're going to switch gears and look at functions e to the x. So there's two rules that we have here, and they're presented both in black here. We know that when we integrate e to the u, du, that's just e to the u plus c. Okay? And when we have a number being multiplied to that x value, and we're taking that integration, we can simplify that as 1 over k times e to the kx plus c. That's how we integrate this type, e to the kx. And you're going to see that in example 3. Okay, so example 3, we're going to integrate x times e to the 3x squared plus 1 dx. So again, I'm going to pick a u, and I'm going to pick 3x squared plus 1. So I have u is equal to 3x squared plus 1. That means the derivative is 6x. So du equals 6x dx. But notice, there is no 6x dx. So that's when we solve for dx. Solving for dx, I get du over 6x. So let's look what we've done. Here's our original integration. So we have the integral of x times e to the u. I'll switch 3x squared plus 1 and put u there. And I know that dx is equal to du over 6, so I switch dx out, replace it, substitute it with du. Once I do that, I see that these x's will become 1. They get rid of one another, cancel out, become 1. All right? So then I'm left with 1/6 e to the u du. So du over 6 is still 1/6, so I brought the 1/6 out, and I'm left with e to the u du. And we know that e to the u du is simply e to the u plus c. So 1/6 e to the u plus c. My u value is 3x squared plus 1, so I substitute 3x squared plus 1 back in for u. Now, how do we take the integral of an exponential function? A to the u, okay, 5 to the x, 2 to the x, 3 to the x. Well, we have a rule that allows us, that involves natural logarithms. I didn't put the proof up here. We'll discuss that in class. But we have the integration of a to the u. Du is simply equal to 1 over the natural log of a times a to the u plus c. So I've given a really generic example, and in the next one we'll look at a little more complicated example involving exponentials. So in example 4, we're looking at integrating 5 to the x dx. So we just immediately look at our rule. So we have an exponential function, so you have 1 over the natural log of a. In this case, a is 5, it's our base. So 1 over the natural log of 5 times 5 to the x plus c, and we're done. Okay? Last example, 2 to the 3x dx. So again, an exponential equation, however, we've switched the power. It's no longer just x, it's being multiplied by something. So again, we're going to use U-Substitution, and we're going to let u equal 3x. So when we do that, u equals 3x, du equals 3, the derivative, and 3 dx equals du. But I don't see 3 dx up here. So again, I solve for dx. I get dx is equal to du over 3. Now, let's rewrite the original problem. The integration of 2 to the 3x dx equals the integral of 2. Instead of writing 3x, I'm going to write u. Instead of dx, I know that dx equals du over 3. So there's my 2 substitution pieces. In for u and in for dx. So now that I have that, I'm going to bring the du over 3. Well, that's just 1/3 du. I'll bring the 1/3 out front, and I'm integrating 2 to the u du, which now I have a definition for, okay, using the natural log. So I have 1/3 times 1 over the natural log of a, which in this case it's 2. 1 over the natural log of 2 times 2 to the u plus c. Notice I can multiply these two fractions together, and I have 1 over 3 times the natural log of 2 times 2 to the u, which is 3x, so there's my substitution of u back in. It's 3x plus c, and using our natural log rules, 3 times the natural log of 2 is just the natural log of 2 cubed, or the natural log of 8. So we have 1 over the natural log of 8 times 2 to the 3x plus c. So I hope you've learned a little bit about integrating natural logarithms, e, and integrals involving exponentials. We'll see you next time.